Here's something a little different. Here's a linear algebra question I'd like to do with you. It's a question about inner product spaces and adjoints. Now, first, you always want to check what the notation in your textbook means. You can usually assume that this curly m is the set of polynomials, but it's good to check that. And here it is in the grab I took from the textbook, that we define curly p of f to be the set of all polynomials with coefficients in f. And I didn't bother grabbing it, but elsewhere it does confirm that when you take the subscript of 2, it means the polynomials with maximum degree of 2. And the r means we are taking our coefficients of these polynomials from the real numbers, so that's fairly straightforward. Once you get used to it, we're taking polynomials of this form with a maximum degree of 2, so an x squared term, potentially an x term, and potentially a constant term. But it doesn't have to have any of those. Similarly, the curly L is the set of linear maps. In the textbook, it's defined the set of all linear maps from V to W is curly L VW. If only one set is given, like here, we assume that it means a linear transformation from P2 of R to P2 of R. So transformation kind of within the same set, or from one set to itself, however you like to think of it. Now, the inner product, this is a chapter on inner product spaces. The inner product is defined this way. It's a little odd, but it is clearly defined, so don't worry about it too much. I'll show you the specific calculations that are required for this question. But in general, what it's having us do is, if you have these two polynomials in P2R, the inner product is defined by multiplying those two polynomials together, integrating to get the indefinite integral, I guess technically. Calculus isn't really my favorite thing. And then evaluating it over the range 1 to 0, and that value is the inner product space. So it does meet all the criteria for an inner product space. You could test that if you wanted. We won't bother because I don't want this video to be an hour long. Okay, so if those concepts aren't familiar, again, there's lots of good resources out there on integrals and inner product spaces, but I'll show you what we're going to do here. Now, we've got this linear transformation, and again, we won't confirm that it's linear, although we could. We have it defined for us, so we'll just use it the way it is. And notice all that this transformation is doing is taking a polynomial, which may have up to 3 terms, and it's pulling out the x term. So that's mapping from P2R to P2R. That's just fine. You could think of this as a flattening or projection of the 3-dimensional space of polynomials onto the 1 dimension that's just the x term. If you think of the A0, A1, A2 as being 3 dimensions in 3-dimensional space, and you're projecting each polynomial just onto its A1 value, that would give you a 1-dimensional space. But that's not what we have to do right here. All we have to do, she says, is show that this transformation T is not self-adjoint. And this is the first question in a chapter where adjoints are defined. You're not going to have an intuitive notion of what this means for a while, so that's fine, don't worry about it. What we will use is this definition of what it means in other words. So this is handy. This is the definition of the adjoint, and we know that self-adjoint means that T star and T are the same thing. So we'll be using this definition here, but we'll be writing T for T star because that's what it means for it to be self-adjoint. T and T star are the same, so we'll just write T. Now, we want to prove that it's not self-adjoint. So just remember, to prove something's true, you need a general proof that will work for all vectors in the space. But to disprove this, we only need to find one case where it doesn't work. So let's look at specific cases. And I know sometimes looking at the general case can guide you towards finding a counterexample, but we're not going to do that in this case. Partly because, if you think about it, if we take 2 completely general polynomials, we could have a0 plus a1x plus a2x squared, and then pick another one to be our w, that would be b0, b1x, b squared x squared. The first thing we're going to do is take the transformation, which is fine, the transformation on the first polynomial will just leave us with a1x, and on the second one it will leave us with b1x. But the next thing we're going to do is multiply those, and we're going to get a fairly big polynomial that we then want to try and integrate. Let's just not bother. Let's just go straight to a specific example. And let's take advantage of the fact that we know that only the middle term of the polynomial is being kept, and let's take advantage of the fact that we can have 0 coefficients in a polynomial. So just the polynomial x is perfectly valid, and under this transformation t, it will just go to x. 1, the number, is a perfectly valid polynomial. Under this transformation, because the 0 coefficient x term is the one that's being taken, the transformation of 1 will be 0. And so these are good candidates for our counterexample right here, because we see that t is going to do something sort of different. Well, of course it does, but it's going to preserve one of these and change one of these. So let's go with this and run through the example, see if it works, and if it doesn't, tweak it to get one that does. So in the first part of our definition, well, let me clean this up a little bit. We're going to say that our vector v is the polynomial x, and our vector w is going to be the polynomial 1. So in the first part of our definition, we want to take the inner product of tv and w. So first t applied to v and w as the inner product. So that's going to be the inner product of, we said that t applied to v, which is x, is just x, so it stays unchanged. And here's our w polynomial. So we want to take the inner product, and we just follow the definition that we were given. This is going to be the integral from 0 to 1 of these two polynomials multiplied, which is just x dx. So the integral of x, I chose this because I know I can do this. This is our integral, and we're evaluating it from 0 to 1, so we have a half minus 0, which is just a half. So see, calculus is not so bad. So now let's do the other side. What is v tw when we do the inner product? Because we want these to not be the same if we want to disprove that they're adjoint. So we're not doing anything to v this time, so that's just x, but we're applying the transformation to w, and we said that that would mean 0. So here we're already in pretty good shape. You might see where this is going. This is the integral, definition of inner product. We multiply these two polynomials together, which gives us 0 dx. We're integrating 0 over a definite interval, so it's a constant from 0 to 1. Well, oops, not that. When you're evaluating a constant, there's no x to put it in. This is just c minus c, which is 0. So we've done what we meant to do, whether we expected to be correct at this point or not. We showed that tvw, the left-hand side, is equal to 1 in this particular case, and the right-hand side, the inner product of v tw, is equal to 0. So since we found a case that these two are not equal, we have proven that t is not self-adjoint. Yay us. And that's all I wanted to say for now. We'll do part B another time. Thank you.